So these are our solutions to the PAT 2023 multiple choice section. So let's get into it. Question 1. What speed does a bull elephant mass 4,900 kilograms have to move at to have the same kinetic energy as a cyclist mass 100 kilograms moving at 30 kilometers per hour? Firstly, if we look at the answers, we'll see they're all in meters per second. So we'll convert our 30 kilometers per hour to meters per second. And we can do this by multiplying it by 1,000 to convert kilometers to meters and dividing by 3,600 to convert to per second. And if we cancel some zeros and simplify a bit, we'll get to that 30 kilometers per hour is 25 over 3 meters per second. And now we can equate the kinetic energies. If we call the speed of the bull elephant v, we get 1 over 2 times 4,900 times v squared is 1 over 2 times 100 times 25 over 3 squared. We can then rearrange for v, and we'll get this. And we can take the square root of both sides, and we'll get that v is 1 over 7 times 25 over 3, which is 1.19. So the answer is B. Question 2. A seed packet contains 100 seeds. When planted, 75 will successfully become plants, but only a third of these will have flowers, and only a fifth of these, only 1/5 will produce fruit. How many seeds produce fruiting plants? So, if we know that only a third of the 75 will become flowers, we can say that 75 times 1 over 3 become flowers. And then we're told only if, and of these, so of this 75 times 1 over 3, only 1/5 produce fruit. So we want to times this whole thing by 1 over 5. And we end up with 75 over 15, which is 5, which means the answer is A. Question 3. Two black holes orbit each other and emit gravitational waves arising from the periodic nature of their orbit. Orbital separation is 10 kilometers. Their relative speeds are close to the speed of light. Gravitational waves travel at the speed of light. Which of the following best describes the frequency of radiation emitted? So because we're told that the gravitational waves arise from the periodic nature of their orbit, we can assume the frequency of the radiation is roughly equal to the frequency of the orbit. So it might be actually we get 2 waves per orbit, or half a wave per orbit, or 1 wave every half orbit. But because all these answers are different by powers of 10 or by 10 cubed, it means that we're just making an order of magnitude estimate. So if we assume like there were 2 waves per orbit or half a wave per orbit, it wouldn't really change our maths. We would just get something slightly further away from the power of 10, but it wouldn't change what power of 10 we're nearest to at all. So we can say the velocity is c, and the radius is 10 to the 4 divided by 2, because their orbital separation is 10 kilometers, and they're going to orbit around their centers. So their radius of orbit will be 10 to the 4 divided by 2 meters. So now we know that v divided by r is its angular frequency, or the angular frequency of both black holes, omega, which is 2 pi times their frequency. Rearranging for their frequency, we get c divided by 2 pi r, which is 3 times 10 to the 8 over pi times 10 to the 4. And at this point, we can just say 3 over pi is going to be roughly 1 because pi is close to 3. So 10 to the 8 divided by 10 to the 4 is just going to be 10 to the 4. So this is going to be roughly 10 to the 4. So it's C. You can put it into your calculator and get the exact answer. But if you're slow with the online calculator, or you're quicker doing it in your head, I think most people are quicker in their head just saying this is roughly 10 to the 4 and putting it into a calculator, then you should just do that, because saving time in the easier questions, or the questions which you don't need to do a long computation for, will give you the time to spend more time on harder questions, or give you time to put a long equation into your calculator when you actually really need to do it. So I'd recommend looking for mental arithmetic shortcuts when you're doing order of magnitude guesses especially. Question 4. The next number in the sequence, 1 over 5, 3 over 25, so on. So looking at this, the denominators look like powers of 5. 5, 25, 125, 125, and 3125. So the weird thing here is that it's 125 twice here, but this could be a simplified fraction. So if we force the power of 5 to appear in the denominator, because that's the pattern we've spotted, we can get it as 15 over 625 by multiplying by 5 on the top and bottom. So now this is our sequence, and our denominators are now powers of 5. That's satisfied. So our denominator is 5 to the n, and our top is 1, 3, 7, 15, 31, which looks like 2 to the n minus 1. This is 2 minus 1, this is 2 squared minus 1, 2 cubed minus 1, and so on. So our nth term is 2 to the n minus 1 divided by 5 to the n, which means our next term is going to be 2 to the 6 minus 1 divided by 5 to the 6, which is 63 over 15,625, which means the answer to this one is E. Question 5. Consider the pulley system in the diagram containing four wheels. If you pull the free-ended distance y, how far will m rise by? So the main bit of logic behind this is that for an ideal pulley, which has a constant tension, it's inextensible, all the stuff you assume in A-level mechanics, the total length of the rope is going to be constant. That makes sense, right? Rope can't appear from nowhere. So if we pull the free-ended distance y, then if we notice that there's four pulleys, we can say that the section of rope, so this section of rope, this section of rope, this section of rope, and this section of rope, the four sections of rope associated with each pulley will have to move a distance y total. And because they're all identical in every single way, their mass per unit length, their tension, they're all going to move the same length, which means they'll each move y over 4, which means mass m is going to be lifted vertically up by y over 4. And this relates to the idea that in these pulley systems we can create, if we are making it easier to lift, so we're using four pulleys here to lift, which means whatever force I put here, I'm going to get 4 times the force lifting. The trade-off is that I can only move a quarter of the distance. If I use 3 pulleys, I'd get 3 times the force and a third of the distance, and so on. So that means they'll move y over 4, so it will be b. If you're still not happy with this, or it seems a bit weird to you, I'd encourage either making like a pulley at school, a basic pulley, or looking at a video of someone doing it, because seeing it in action really does help with your understanding if you can't visualize it well or think about it that well. Question 6. Consider f of x is equal to x squared. You want to transform the function so you get a new function, g of x, stretched by a vertical scale factor of 2 with a line of symmetry about x equals 1 and which is never positive. G of x is which of the following functions? So we know f of x squared is always positive. So to make sure it's never positive, we want to multiply by minus 2, as that does our vertical stretching as well. And if we want a symmetry about x equals 1, we know quadratics are symmetric about their midpoint, or their turning point, so their minimum or maximum. And if we want it to be symmetric about x equals 1, we want the turning point to occur at x equals 1, so we want it to be x minus 1 squared. And minus 2x minus 1 squared, which is g of x, is just minus 2 times f of x minus 1, which means the answer to this one is A. Question 7. We're given y is equal to 2 plus x over 2 all to the power of 4, and we're asked to find dy by dx. So when I'm looking at all these answers, I'm seeing that all the constant terms are different, which means I only need to work out the constant term, my derivative, and then I can match it up. So the derivative using the chain rule is going to be 4 times 1 over 2, 2 plus x over 2 to the power of 3. And then that's going to be 2. Then 2 cubed is going to give us 8 plus some x squared term, some x term, and an x cubed term. So that means the constant will be 2 times 8, which is 16. So the answer has to be D. Question 8. All resistors in the circuit below have the same value. You can call that R. If an ammeter is placed in a circuit at points A through to E, which are all labelled, which are the following set of points will give the same reading? So as this first branch has the same resistance and this second branch, they're all just made of one resistor in parallel, we know the current will split equally for each branch. So the current in A will be half of I if we say I is the current in the circuit, and the current in B will be a quarter of I. And then in the third branch, we have some series resistors as well as parallel resistors, so we can simplify it to this, having R, 2R, and 2R here. However, another thing we can say, at E, the current is going to be just I, because it all rejoins there, Kirchhoff's current law. And now we have R, 2R, and 2R. We can simplify these two R's in parallel to an R, and then we'd have an R and an R, and we know the current is going to be equal. So we know the current in C is going to be I over 2, and the current in this simplified branch, or the total current in this bottom 2R branch, is going to be I over 2. And as the current in each 2R is going to be equal, we can just say if 2I is the total current, or if I over 2 is the total current, the current in each branch will be I over 4. And we can also apply Kirchhoff's voltage law to the loops and get the same relationship that the current in C is 2 times the current in D, and the current in C is half the total current, and which means the current in D is I over 4. So then we can see that B and D are the same, and A and C are the same, and there's not an option which has B and D in this multiple choice. There is one that has A and C, which means it's going to be that one, so the answer will be B. Question 9. If dy over dx is x squared plus 1 over x cubed, and y equals 0 and x is 1, what is the integral between 1 and 3 of y dx? So we can say that the derivative of y with respect to x is x squared plus x to the minus 3. And then if we integrate this, we can get that y is 1 over 3x cubed minus 1 over 2x to the minus 2 plus c. And then we know that 1, 0 lies on this curve. So we say that 0 is 1 over 3 minus 1 over 2 plus c, which gives us c as a sixth. And now the integral between 1 and 3 of y dx is the integral between 1 and 3 of the expression we found for y, which ends up being this. You can see the algebra here. I'm not going to speak for every step. I've done a couple lines of working here just to show you the working out if you don't want to do it on your calculator. Like I said, if you're not comfortable with online calculator and you want to try just do it with mental arithmetic, you can cancel out a 3 on here and you end up with 3 cubed over 4. And then combine the rest of the terms is mostly easy. And you end up with 80 over 12, which is 20 over 3, which is going to be C. And just here's the working in if you just want to pause it. Okay, question 10. Particle of mass m travelling freely at initial speed v can be stopped in a distance d by a constant retarding force F. What is the magnitude? What magnitude of force applied in a direction perpendicular to the motion? So when I'm seeing in a direction perpendicular to the motion, I know that's going to be centripetal, a circular motion. It's going to be a centripetal force if my force is perpendicular to my velocity or my direction of motion. And we're asked what magnitude of force would to cause circular motion would be needed to change the trajectory. Yeah, so they just I jumped the gun there, but what magnitude of force would be needed to change the trajectory at the same speed into a circular arc of radius d? So we know that F times d is going to be the kinetic energy because this constant force stops in a distance d and it does work Fd, which must be equal to its kinetic energy. This gives us that F is mv squared over d times 1 over 2. And the centripetal force required is mv squared over r, which in this case is mv squared over d. And we can see that as just 2 times this force. So our centripetal force is going to be 2F, which is going to be E. 11. What is the integer m such that the sum from n equals 1 to m of 3 plus 2n is 140? So there's two ways we can do this. We can split our sum up into the sum from 1 to m of 3 plus 2 times the sum of n is 1 to m of n. Or you could evaluate the first term, the second term up to m, and you'd see it's an arithmetic sequence. But I've split it up here and I've used the standard results. If you're not doing further maths, you might not know the result for the sum of 1 to n of r is just n plus 1 over 2. I think it's useful to know it's not too hard to remember, and you can even derive it using arithmetic series. So I'd remember it, and it makes it easier when we split it up. And then the sum of 3 from n equals 1 to m is just going to be 3m, because we're doing 3 plus 3 plus 3 plus 3m times. So now we have 3m plus m plus 1, because the 2's cancel, is 140. We can expand this and get a quadratic, and we will get m equals minus 14 or m equals 10. And of course, it has to be positive, because we can't sum from 1 to something smaller than 1 minus 14. So it's going to be C, m equals 10. Question 12, the last question for the multiple choice. A device uses 3 kilowatts of power at a voltage of 60 volts. It's connected to a power supply via an ideal transformer. The transformer has n turns on the winding connected to the device and 20 turns on the winding connected to the power supply. What current flows in the winding connected to the power supply? So we are told the transformer is ideal, which means its efficiency, which you can use this Greek n eta, sometimes to represent, is 1. And all that means is the input of the output power, which is the current is secondary times the voltage across the secondary, is equal to the input power, which is I primary V primary, which means the IS VS is IP VP. So then we get the secondary current divided by the primary current is the primary voltage divided by the secondary voltage, which we know is the number of turns on the primary divided by the number of turns on the secondary. And with this question, what it's important to do is we need to identify what actually is our primary coil and what is our secondary coil. We can see an answer of like 1 kiloamp is going to be unreasonable, but the rest of these are all pretty reasonable. Maybe 50 amps is a bit too high, but we can't really say. So our device is going to be our secondary coil. And so we see the device, which uses 3 kilowatts of power at this voltage, that's secondary. And we're told that the transformer has n turns connected to the device, our secondary coil, and 20 turns on the one connected to the winding, on the winding connected to the power supply, which we're going to call our primary coil. So underlining this stuff and saying whether it's secondary or primary just helps me when I'm plugging my numbers in, as I'm not going to mess up IS and IP or VS and VP. It's like or the number of turns, because I can just look at what I've written on the question. So first we can find the secondary current by doing 3000 divided by 60 to find it as 50. And then we can just use our equation to get the primary current is going to be the secondary current times the secondary turns over the primary turns. If we look at this, we say n turns on the secondary and 20 n on the primary terms, on the 20 turns on the primary coil. So we'll get 50 times n over 20 n, which is going to be 5 over 2, which means the answer to this one is going to be C. I'll just leave the work in there again for a second. And that is all of the multiple choice. So these are solutions to the long response questions on the 2023 PAT paper. And we're starting with question 13. We use some measure scales to discover the following relationship between the mass of apples MA, bananas MB, and carrots MC. And we're given these two equations, which we can label with a star and a plus. We're asked to find all the combination of apples and or bananas that have the same mass as 5 carrots. So what we're going to want to do is get the mass of an apple and mass of a banana in terms of the mass of a carrot. And then we want to say that that sum is going to equal 5 carrots, 5 MC. So the first equation, we cancel out 3mb on both sides, and we get that MC is 2ma after collecting like terms. And the bottom equation gives us the mass of an apple plus mass of a carrot is 4mb. And we can use the above relationship we got from the star equation to find that 3 over 2 MC is 4mb. So the mass of a banana is 3/8 the mass of a carrot. And now we can write out what we know again neatly. The mass of an apple is the mass of a carrot over 2, and the mass of a banana is 3/8 the mass of a carrot. Now, the combinations that we want to think of are ones which are going to be equal to 5 times the mass of a carrot. So we want some integer multiple of 1 over 2 plus some integer multiple of 3 over 8 to equal 5. And what we can deduce from this is that MB has to be a multiple of 4, as this will reduce our denominator 8. We'll be able to cancel out a 4 in the denominator, and we'll have a half, because we can't add 8 to a certain number of halves and get a whole number. So the first multiple of 4 is 0. So if we have 0 bananas, then we need MC over 2 is 5MC, or KMC over 2 is 5MC. So we get that K is 10. So our first case is 10 apples and no bananas. And our second case, when we have 4 bananas, is, it's written as the fourth case here. When we have 4 bananas, that means we're going to have 3 over 2 carrots in terms of our bananas, which means we're going to need 7 apples to ensure that our sum is 5 MC. And then our second case here, when we have the next multiple of 4 is 8. When we have 8 bananas, we're going to need 4 apples. And our final case is when we have 12 bananas, we're going to need 1 apple. And if we go to 16 bananas, we'll see that the equivalent mass is actually 6 carrots, which means any more multiples of 4, we're going to have too much mass in our bananas, and we're not going to be able to have a positive integer amount of apples, which gets us to 5 carrots. So we can also, as long as this deduction of it being a multiple of 4, we do a similar thing here. You can read that if you want. And yeah. Question 14. This one, it's just simultaneous equations disguised. So what we want to do is write 16 is 2 to the power of 4, and then we can just get x plus 2y is 4 and xy is 2. We can rearrange for x or y, and we'll get a quadratic, and we'll see that this is a perfect square, so there's only one y value. So we find y is 1 and x is 2. Question 15. A ball of mass m sits in equilibrium on top of a set of 3 identical springs of spring constant k, shown in the diagram below, and we're told to assume the springs are stiff and that the ball is light. The ball is pressed down by a distance x and then released, and we're told that 90% of the elastic energy is converted to the ball's kinetic and gravitational energy, and we're asked to find how high the ball will go above its point of release in terms of m, k, x, and g. So we need to just quickly think that the maximum height of the ball is going to be when its kinetic energy is 0. So that's going to be how high it will go above its point of release. And now we need to first simplify our spring system, because we can't really work with springs like this. We can simplify the two springs in parallel to a spring of 2k, as in parallel the effective spring constant is just the sum of the spring constants. And then in series, we can say that the effective spring constant we can call k prime is 1 over k plus 1 over 2k all to the minus 1. which is 2k over 3. And now what we need to realize is that this ball is actually going to compress a little bit just by being on top of the springs. So we need to find that compression, and we say at equilibrium there's going to be no resultant force on it, so its weight is going to be balanced by the spring force, k prime e. That means that the equilibrium extension is going to be mg over k prime. And after a further compression, the total compression is going to be E plus X. X is how far we've pushed it down, they said in the question, which means our elastic energy is 1 over 2 K prime E plus X all squared. And then we can say 0.9 times this elastic energy goes to mgh, and we can rearrange for h max down here. But one thing we can note is that because we're told the ball is light, we can say either here at step 2 or at step 4, we can say that E, mg over k prime is roughly equal to 0. So the answer could also be 3k over 10 mg, or multiplied by x squared. And that is valid because of what we're told. We're told to assume the ball is light. But if you don't say why you're ignoring it, you just ignore it, it's not clear that you've understood that. So it's important to do this working anyway, or to just say at this point E is roughly 0. So then when you follow through the rest of your working out, it shows that you haven't just missed something and you've actually thought about why you're given the assumption. Because they could easily ask this question without that assumption of the ball being light, and then you'd need to include this definitely. Question 16. In astrophysics, the Jeans length, lambda j, is a measure of the size of a cloud of gas. And then it tells us a bunch of extra stuff. It tells us it depends on the speed of the sound in the gas, the gravitational constant, and it gives us that in base units, fundamental base units, and the density of the cloud, rho. The dependencies may be expressed in some form, c to the alpha, g to the beta, rho to the gamma. And we're asked for the values of alpha, beta, gamma, for which are required for the gene length to have the dimensions of length, which are meters. So firstly, we can write down the dimensions of everything we're given. The dimensions of the fundamental constant g, the gravitational constant, are going to be L cubed, because we have meters cubed, so length cubed, mass to the -1, kilogram to the -1, and time to the -2, seconds to the -2. The units of C are going to be meters per second, so L T to the -1, and density is going to be kilograms per meter cubed, so M L to the -3. And now we can say that the dimensions of, that's what these square brackets are used to show, the dimensions of our quantity, or the units. So the dimensions of our wavelength are going to be C to the alpha, G to the beta, rho to the gamma, all of these dimensions to their powers, which is L to the alpha, T to the alpha, and so on for G and rho. And now we know that the length needs to sum to 1 because the only dimension of lambda is m. So alpha plus 3 beta minus 3 gamma, which is the total length power, because when we're multiplying our quantities, kilogram times kilogram is kilogram squared, meter times meter is meter squared, so we just add the powers like you normally do with index rules. And then for t, our total power needs to be 0, and for m, our total power also needs to be 0. So from m, we can take this top bottom equation, multiply it by 3, and add it to L, and then we get alpha is 1, and then we can use the bottom equation to get gamma is a half, and beta is minus a half, or gamma is minus a half, and beta is minus a half. So once you form these equations, solving them is quite easy. They're nice equations, that's not the important part. The important part is writing everything in terms of the units and saying the meter unit or the length unit has to be 1, the time unit has to be 0, and the mass unit also has to be 0. And then we can write down here, if you want, that the wavelength is proportional to the speed of sound divided by GP, because these are both to the power of minus a half, so we can just write them under the same square root sign. And the proportional sign is quite important here. It wouldn't affect the marks you get because you only asked about the values of alpha, beta, and gamma, but all this has shown us is that it's some constant times this, because constants can be dimensionless. So we can't, if we use proportional, that's proper mathematically. Okay, 17 now. A mass m on the end of a rigid rod of negligible mass hangs from a pivot point. The pivot moves horizontally to speed v, and the mass experiences a drag force f of v in the direction opposite to its velocity. At speed v, the rod makes a constant angle theta to the vertical. Find an expression for f of v in terms of the angle theta that the pendulum makes to the vertical. And then we're asked to sketch theta as a function of v in the case that f of v is proportional to v. So there's two ways we can do this. Firstly, we can look at the mass, which we know is also moving at a constant horizontal speed because it is attached to the pivot and the pivot is not moving. So if the pivot moves a bit to the right, the mass will move a bit to the right. And that means the forces on the mass are zero. So if we say there's a tension T in this rigid rod, we get that horizontally, F of V is equal to T sine theta, and vertically, mg is T cos theta. We can then divide these equations and we'll get F of V over mg is tan theta, so F of V is mg tan theta. And we can also do this with moments, because we know that as this is moving at constant velocity and m is not rotating about here, there's going to be no rotation about this pivot point. So the total moment about the pivot point is zero. So we can break up mg into these two components. We know that only the component which is not parallel, that doesn't pass through the pivot, will cause a moment, which is mg sine theta. And we know it's a distance L from the pivot. So we know mg sine theta L is equal to f of v times cos theta L, because the component of f of v, which causes rotation, which causes a moment, is the cos component, because that's perpendicular to the pivot. And then we rearrange to get f of v as mg tan theta. Both go for the same answer. So if you have time to do it, you can do both methods if it gives you some reassurance. But either method works. It's just good to know that both of them work and why they both work. So part B, we're sketching theta as a function of v in the case that f of v is proportional to v. So if f of v is proportional to v, it's just kv. And we know from this equation that theta is going to be inverse tan of f of v over mg, which will just be some constant times v. So then we can then plot this graph here with these asymptotes plus or minus k, which are going to be plus or minus pi over 2 in this context, because we know that, well, the sign of it will just mean whether it's clockwise or anti-clockwise, or to the left or right of the vertical. And when it gets to pi over 2, we know that's impossible because you can't have a mass supported horizontally, as there will need to be some force balancing its weight. So we can't just have a mass flying horizontally with no upwards force on it. 18 now. A quartic polynomial function f of x has these following properties. The second derivative is 0 at these points only, nothing else. The first derivative is 0 at 2 and some other points, maybe we're not told them. And we're told that f of 0 is 0 and f of 1 is 3. So if f of x is quartic, we know that the second derivative is a quadratic. And we could here start also with some quartic equation, but then we're going to have very long simultaneous equations, which you don't want to deal with in an exam. You can easily make mistakes in those. So what we can do with is start by writing f of x, or the second derivative of f of x, as some quadratic, which we know is going to be x minus 1, x minus 3, which means the second derivative is x squared minus 4x plus 3. An important thing to note here is there could be a constant in front of all of this, but when we're solving our equation equal to 0, our constant doesn't matter, and when we're differentiating, our constant doesn't matter because we can take the constant out to the front. So that means the derivative of a f of x is also a times the derivative of f of x. So when we're dealing with equals to 0, we can ignore our constant and introduce it once we're dealing with non-zero equals, because then our scaling is going to matter, because that's all our constant does to our graph and our derivatives. It vertically scales it. So we now can integrate this f double dash of x to get the first derivative of x is x cubed over 3 minus 2x squared plus 3x plus c1. Obviously all multiplied by a constant, but as it's equal to 0, that constant will disappear, it doesn't matter. And we can get c1 is minus 2 over 3 by using at x equals 2, the derivative is 0. Now we need to integrate it again, and we'll get this expression plus c2. And we can use f of 0 is equal to 0 to find c2. c2 is 0. And now we need to scale it by some amount a. And when we find out how much a is, we can just use the fact that f of 1 is 3. So we can say 3 is equal to, just plug in x equals 1. And then that gives us a over 4 is 3, so a is 12. We plug 12 back into f of x, and we get the quartic polynomial we desire. That's 7 marks. It's just a lot of algebra, and you have to think about smart ways to do it. So not starting with a quartic polynomial, which is going to be very messy, and dealing with the constants later because of the reasons I discussed. And then this question is quite nice, actually. 19 now, we're asked to solve the following equation for real x. This is, again, probably an AS maths question, maybe A level. It's just a hidden quadratic. We can show that explicitly here by writing it as e to the x squared. And then we can factorize it. We can guess the factors, because you don't really have your calculator to solve it if you're using the online calculator. So you can say our product needs to be 15. We need to get 6 on our squared term, and then the sum is 1. So we'll find that we have plus 5 and minus 3, and then 3 e to the x here and 2 e to the x here. which gives us these two solutions, but we know that e to the x for real numbers is always positive, so we ignore the negative solution and we take the inverse exponential, so log of both sides, and get ln 3 over 2 for x, and that's the only solution. Question 20 now. A diver 5 meters under the surface of the sea looks up. They see a circle of light directly above them, where they can see what is on the surface, but outside of this circle, the diver only sees a reflection of what is under the water. Explain why there is such a circle and calculate its radius. So, this diagram here at the top is showing what's actually happening. The diver's eye is down here, and he is looking up and he's seeing a circle of light above him. And then why this is happening is shown underneath. The diver here, there are rays of light leaving or entering his eye. Obviously, to see, they need to enter his eye. But a useful thing about optics is if we reverse the path of the ray, it's going to be identical. So if these lights are coming to hit him or going away from his eyes, it's the same. And what's going to happen is light is going to refract out and he's going to be able to see what is ever on the surface until it gets to the critical angle here, where light is actually going to refract along the boundary. That's what this third one shows. And then this fourth line is showing when TIR is happening, total internal reflection, so he cannot see out, sadly. And we know he's 5 meters below the surface, and we're given the refractive indices of water and air. So we can find the critical angle to be 48.8 degrees. And then using this triangle, which we've just took this circle and we've sliced it at any point, because of course the radius is going to be constant, we calculate the radius, and then we just say the area is going to be pi r squared. But we only need to calculate the radius. But if they ask you to find the area, it's obviously just pi r squared. So yeah, that's the radius. Question 21. We're asked to find all values of x that satisfy this equation. So we can expand our brackets out. We can use the sine squared plus cos squared equals 1 identity to get a cubic in terms of sine x. And then you can do a nice thing here. If you actually spot this, you can group to factorize. So we can take a 4 sine squared out of the first two terms and a 3 out of the second two terms. And we actually get sine x minus 1 being common to this. So we can now factor sine x minus 1 out of the whole thing and have our factorized cubic as this. But you might not see that, so you can also just guess the factors of 3 as solutions. And as we know at sine x, we know that sine x being equal to 3 or minus 3 can't happen for real values of x. So we will guess plus 1, minus 1. We'll find plus 1 as a solution, and then you can do whatever way you like to find your other two solutions. So now we have sine x is 1 or sine x is plus or minus square root of 3 over 2. And we want all the solutions, so we want to find the general solution. So for sine x is 1, it's just going to be pi over 2 plus or minus 2 pi n, where n is an integer, so minus 1, 2, whatever. If we do all the integers, that will give us every solution. And then for plus or minus square root of 3 over 2, we can find the two principal solutions for the positive solution. So sine x is positive square root of 3 over 2. Our principal solutions are pi over 3 and 2 pi over 3. And then we can actually just add pi to these across all integers, because sine of pi plus x is minus sine of x. So adding pi is going to hit the negative solutions as well. You could also write this in terms of the negative principles plus 2 pi, and then you'd have an extra 2 x is equal to things down here, but this is neater, and it's neater, so that's why we do it like this. But you'd get marks for doing it the other way as well. Now we're at 22, and two identical spacecraft of mass m are in stable circular orbits around the Earth, one at a height of RE and the other at a height of 2 RE above the surface of the Earth. That's keywording, and you always need to look out for it in questions when it's something like energy, because they're always going to trick you. Or not trick you, they're going to try to trick you. You're not going to fall for it. We're asked to find the difference in total energy between the two spacecraft. The radius of the Earth is RE. So we can derive the total energy for an orbiting satellite first at a general radius r. And we do this by equating the centripetal force, mv squared over r, to gravity, because that's all that's causing it in the circular orbit. And we find that the velocity squared is gm over r. And we know our total energy is kinetic plus the potential. Potential is obviously negative by its definition. So we get the total energy of an orbiting satellite is minus 1 over 2 gmm over r. And that's for a radius r. So the change in energy at these two heights is going to be minus 1 over 2 gmm over r, and I factored the minus out. It's going to be the difference, so 1 over r1 minus 1 over r2. And r1 is going to be 3 re, and r2 is going to be 2 re. You see how we've added plus re here, because it's at a height above the surface of the Earth. So the distance from the center of the Earth, which is our radius of the orbit, is going to be whatever the height is plus RE. So then our difference in energy becomes minus 1 over 2, 1 over 3, minus 1 over 2 GMM, brackets 1 over 3 RE minus 1 over 2 RE, which is just GMM over 12 RE. And if you did your R1 and R2 the other way around, you just get this negative, and it just says the difference in the total energy. So if you quote the positive one or the negative one, it'll be fine. Question 23 now. A beam of light in a medium with refractive index M1 is incident angle θ1 on a slab of material thickness D with refractive index N2 is greater than M1. This is shown in the figure, and the rear surface of the slab is mirrored and perfectly reflective. So question A is, what distance L does the beam transmitted into the slab travel before re-emerging from it? Express your answers in terms of N1, N2, θ1, and D. So we can draw what's happening over here, and we can see that the length it travels is going to be 2d over cos θ2. We can use the law of reflection here to say this angle is also θ2, and then it's just trigonometry to find the actual path length in terms of d and thetas for now θ2. Then to get θ2 in terms of θ1 and the refractive indices, we need to use Snell's law. So n1 sine θ1 is n2 sine θ2, and then we can get that sine θ2 is n1 over n2 sine θ1. So θ2 is going to be inverse sine of all of that, and inverse sine of all of that is actually just some angle. So the fact that cos squared of some angle theta plus sine squared of some angle theta is 1 means we can rewrite cos of some angle as the square root of 1 minus sine squared of that angle. And we know that sine of arc sine is going to cancel out, so we're just going to be left with this angle squared, or not this angle, left with this expression squared. So we're going to get 2d over the square root of 1 minus n1 over n2 sine 1 theta all squared. And the step's not shown using cos squared theta plus sine squared theta, so if you need to write that out to convince yourself, you should. Yeah. So now we're asked for the limiting values of L at large and small θ1. So when θ1 is 0, L is just 2d. And for a maximum L, we want the θ2 to be the critical angle, because as n2 is greater than m1, when going from n2 to m1, total internal reflection is going to be able to occur. So this will occur when sine θ1 is 1, so θ1 is 90. So and our critical angle is going to be n1 over n2. And that means our distance is going to be infinity when it's doing total internal reflection. It's going to stay inside and just keep on reflecting. But according to this equation we've written, when θ1 is 90, we just get L is 1 over the square root of n1 over n2 all squared. So you can say according to your the model, that's what you get. Then you can say in reality, when it gets to total internal reflection, it's going to just keep on reflecting. It's going to stay inside n2, so the distance will be infinity. Now we're asked to consider the case in which light of wavelength in medium 1, lambda 1, is incident normally. So one thing we can remember here is that frequency stays the same when traveling to different mediums, but the speed and the wavelength are going to change. And we're asked for what values of d would light reflect from the two surfaces interfere constructively. So we want this extra path difference here, travelled in n2, 2d, to be an integer multiple of the wavelength in n2, because that means it's going to leave exactly where it started, and so it's going to interfere constructively. And we know that n1 lambda 1 is n2 lambda 2, because this is because n1 lambda 1 is the wavelength in a vacuum, and n2 lambda 2 is also the wavelength in a vacuum. And that means the relationship we require is 2d is k lambda 2, so d is k over 2 lambda 2, and that is the same as k over 2 n1 over n2 lambda 1, which is what we want. Well, it's not what we want, it's expressed in lambda 1 and n1. You could probably express it in terms of lambda 2, but I interpret the question as asking for in terms of n1 and n2 and lambda 1. Just one more note on this one actually, is normally you do have a phase change at a boundary, so we're ignoring this and we're going to assume, or we're ignoring it like we're told, and we're assuming that they just mean the wave comes back on itself without flipping or changing its phase at all. 24 now. For a ship floating at anchor, so first thing to notice is that ship is anchored, so the ship can only move vertically, and like it tells us, the ship moves vertically. As waves on the surface of the sea cause the height to vary with the position x and time t, as y of xt is this sine function. So the first thing we can notice is that for a constant x position, this looks like a sine omega t plus phi, which is simple harmonic motion. So all of these particles, or at a constant x position, the waves, or the particles of the water, I guess, are oscillating up and down with simple harmonic motion. And A, lambda, and V are positive constants. We're told that the period P of the ship's, well, we're asked for the period P of the ship's vertical oscillations. So an important thing, we've already said, the ship is anchored, and this is the waves that are moving along the surface height. But the ship's going to move in phase with the waves, of course. When the waves are low, the ship will be low. When the waves are at the equilibrium, the ship will be at equilibrium. And then when the waves are high, the ship will be high. So we can say that x minus v t1 over lambda is 2 pi, and then x minus v t2 over lambda is 4 pi. That's not been shown, but we've just cancelled the pi's out and the 2's in some cases. Or yeah, the 2 here, and then there's 4 divided by 2 here, which is 2. And then we can subtract these two equations, and we know the time difference is going to be 1 period because the period of sine is 2 pi, and we've went from 2 pi to 4 pi. And we do our algebra, and we get that v delta t, which is our period, is lambda. So our period is lambda over v. And then we can also do, this is just a shorter method of the same thing really. For a constant x, 2 pi over lambda v t1 minus t2, I've just cancelled these x out straight away because I know they're constant, is 2 pi. So then t1 minus t2 is p, which is lambda over v. And one more way you can do this quite quickly is for a constant x, we know that all of this is constant. And the period of the constants in like sine of x plus k, that constant only shifts it left and right. The constant which actually affects the time period is the multiple in front of what we're changing. So in this case, t. So 2 pi over lambda times v is what's going to be changing our time period in this case. And then we can just use that to say, to find out the reduced time period or the change time period. The same way in maths, if you have like sine of 5x, you'll say the period is going to be reduced by a fifth. So 5x is whatever, and then you rearrange. And then B, what total vertical distance does the ship move through during a time interval equal to p? So we know it goes up, down, down, up if it's starting from equilibrium. If it's not, it's going to do the same thing, but it's just going to end at a different place. And we know the total distance is going to be 4 times the amplitude. And lastly, we're sketching the ship's kinetic energy. Once again, we're talking about the ship in all of these cases, not the waves. Kinetic potential energies as functions of time on the same plot from t equals 0 to t equals 2p. So we don't know anything about the ship's x position, but we do know that the ship's x position is not going to change because it is anchored. So we can assume that the ship's x position is non-zero to be more general, and we sketch our kinetic energy in red, which we know is always positive, and our potential energy in black, which can go negative if we define the equilibrium position of the ship as zero potential energy. Just we could have written here, taking the equilibrium point as zero potential energy, so below is negative and above is positive. And then we see that when our potential energy is zero, our kinetic energy will be maximum. And when our potential energy is maximum in magnitude, our kinetic energy is going to be zero. Just getting that to roughly line up is the most important thing here. And it's over 2 time periods as well. So whatever happens in this first time period is just going to be mimicked in the next time period. And then our 0 points are going to be when our 2 pi over lambda x minus vt is k pi, because we know sine is 0 at pi, 2 pi, 3 pi, 4 pi. So if we set this expression on the inside for a constant x equal to pi, we can rearrange to get that t is x minus n over 2 lambda over v, where n is an integer. And that's going to be the 0 points for our y displacement. And the 0 points for our y displacement are 0 points for our potential energy, because we said our potential energy, the new 0 point is going to be at the equilibrium. And that's obviously, that means our kinetic energy will be maximum, because the total energy of this ship is going to be constant, oscillating up and down. 25 now. 25 is just a maths question. It's quite nice. 7 marks. It's a lot of marks. Obviously, Obviously, the multiple choice questions are going to be different. You might not get big 7 markers, but just knowing how to work through this maths quickly is going to be useful. So we're asked to sketch y equals x to the 4 minus 2x cubed, which we can factorize as this, and y equals 2x minus x squared, which we know is just a quadratic. We can factor it like this on the same axes. And we want to show the nature of the stationary points, label their coordinates, and write down an integral expression for the finite area enclosed between the two curves. You do not need to evaluate the integral. So, firstly, if we look at this first curve, we take the derivative. We call this first curve y1.
and we find that the derivative is 0, x equals 0, and x equals 3 over 2. Then our second derivative tells us that when x equals 0, the second derivative is 0, so x equals 0 is an inflection. And when x equals 3 over 2, we're going to get a minimum point, as our second derivative is going to be positive. So now we know that this 3 over 2 is going to be a minimum, and this 0, 0 is going to be an inflection. And we know sketching our quadratic here, it's just going to be a quadratic with roots at 0 and 2, and the turning point at 1. And when x is 1, the value is going to be 2 minus 1, which is 1. So we can sketch y2 quite nicely. And then we know y2, for positive x, it's going to be really positive, we get close to infinity. And then for large negative x, it's going to go to negative infinity as well. So it just looks like this, with an inflection at 0, 0, and then goes down to 3 over 2, the minimum, and then it goes back up. And the finite area between the two curves will be the area from 0 to 2 of this y2 curve, 2x minus x squared, subtract the area from 0 to 2 of this other curve. The reason we're subtracting is because for y1, the area is going to be negative, and we want to add the area, so we can reverse that by just subtracting it, and then minus times minus will give us the magnitude of the area. So it will be 2x minus x squared, subtract x to the 4 plus 2x cubed, because we're applying the minus to the whole thing with respect to x. And that is an integral you can evaluate. We're not asked to do it. So that's it for this question. Question 26 now, final question. Two separate pairs of unbiased dice are rolled. One pair consists of two 8-sided dice with face numbered 1 to 8, and the other pair consists of one 6-sided die with face numbered 1 to 6, and one 10-sided die with faces numbered 1 to 10. Which pair is most likely to show a total of 16? We know the total number of outcomes for the 8 dice is going to be 64, 8 times 8, and the total number of outcomes for the 1, 6 and 1, 10 dice are 1 to 6 and 1 to 10 dice is going to be 60 because of 6 times 10, the total number of options. And there's only one way to get 16 for both of them. For the 8 die, it's going to be 8 and 8, and for the 6, 10, it's going to be a 6 and 10. So the chance is 1 over nm for each die, where n and m are the number of faces. For the 8, it's 64. For the 6, 10, it's 60. 1 over 60 is greater than 1 over 64, so the 6, 10 is more likely. Part B. Are any totals equally likely to be rolled using the two pairs of dice? So for this we require k over 60 is c over 64, where k is the number of ways we can get an outcome for the 10 and 6 die, and c is the number of ways we can get an outcome for the 8 die. And this is only possible, of course k and c must be integers, there's only a whole number of ways we can get a certain outcome. For the integers, this is only possible when k is 30 and c is 32, or when k is 15 and c is 16, which means our probability of getting a certain number needs to be 1 over 4 or 1 over 2. And this is impossible to happen, or this cannot happen, as there is no way to get the same number of total greater than or equal 15 times from 2 dice. That makes sense because you think we're only going to have 60 or 64 rolls. There's no way that half of these rolls can be the same number, or even a quarter of these rolls, because of all the different combinations we can get. So the answer is no. And now we're asked for the smallest total that is more probable when using the pair consisting of 8-sided dice. So, first thing is this is done down here because this is a bit longer. The first thing we can note is that up to 7, there's an identical number of ways to get each total, as all the outcomes are the same, because we can get a 6. So say our total was 5, we can get a 4 and a 1, a 3 and a 2, a 2 and a 3, and all of these, the 8, 8 and the 10, 6 are going to be able to do that in the exact same amount of ways. And as 60 is smaller than 64, that means the probability for the 10, 6 die is going to be greater, up to 7. And then when the total is 8, the 10, 6 can only make 7, 1 in one way, as this 6 die cannot roll a 7, but the 8, 8 can do it in two ways, as either of these dice could roll a 7 and the other one gets a 1. So if we list out all the combinations which add to 8, 7, 1, 6, 2, 5, 3, 4, 4, so on, we see that there's 7 total for the 8, 8 die, this should say, and there's only 6 total for the 10, 6 die, because we get rid of one of these 1, 7 or 7, 1 pairs. And that means that the probability for the 8, 8 die is 7 over 64. For the 10, 6 die, it's 6 over 60. Comparing these fractions, you can just subtract them on your calculator. You can use known fractions, which might be a bit easier. We'll get the 7 over 64 is greater than 6 over 60. So for the total is equal to 8, the probability for the 8-sided dice is greater, and that's the smallest total because we've said up to 7, the total is identical, or the probabilities, the number of ways you can get a total is identical. So the probability is always greater for the 10 and 6 dice. Question D now. Which pair is more likely to give a total that is divisible by 3? So we know up to 6, there's going to be the same number of ways we can get both the combinations, and so the probability is the same because the same number of ways. And then 10 for 9, the 6, 10 can get it in 6 ways. The 8, 8 can get it in 8 ways. For 12, the 10, 6 can get it in 6 ways. The 8, 8 can get it in 6 ways. For 15, the 6, 10 can get it in 2, and the 8, 8 can get it in 2. And when we add these up and we compare the denominators, so we do this plus this plus this over 64, and this plus this over 60, we'll find that the 8, 8 dice are more likely. And last question now. Given that at least one of the 8-sided dice has landed on a 5, is a total of 10 or 11 more likely? So if one has landed on a 5, to get 10, the other one needs to be a 5. But if the total is 11, we could get a 5, 6 or a 6, 5. As there is more options for this total to be 11, there's going to be a higher chance, so that 11 is the more likely total, given that 1 is a 5. Because we know given that 1 is a 5 restricts our sample space to the probabilities or the rows which have at least 1 5 there. And then we just we need to find which total is more likely. So that is the end of this paper. This final question 26, it's a lot of short questions, so you could definitely see something like this in the multiple choice for the 2024 paper, because it's only going to be multiple choice. I hope the paper was useful. If you have any more questions or you're confused about anything, just comment that. I'll be sure to help. And good luck with the pattern you sit.